Okay, so we are going to do the entry task for Wednesday and Thursday's Zoom class that we did. So just remember there's two equations this week that we're working on. It's the impulse equation, which is J equals F times T, or force multiplied by time. So J is impulse, force is F is force, and T is time. And then also the J equals change in momentum, or impulse equals change in a momentum equation. Since J is F times T, we just did that here, and change in momentum, or momentum, is mass times velocity. And remember, this is technically a change in velocity. I just don't always put the delta there just so we can make it real simple when we're doing the equation. But remember, it is a delta V, or change in velocity, because you can't have a change in momentum unless you have a change in velocity. And since mass of an object stays the same, the velocity is what changes when you have a change in momentum. Okay, so the lesson explains more, so make sure you've watched that. All right, so a soccer player kicks a ball with 75 newtons of force. Find the impulse, so that's what we're looking for, on the ball if his foot contacts the ball for 0.008 seconds. Now remember, that's a really, really small time, because if you think about kicking a soccer ball, your foot is not going to be in contact with the ball very long if you're trying to kick it hard. If you're kicking it softer, you may have more contact or more time with the ball in contact with your foot. But think about scenarios when you're reading these. If you're wondering why the numbers are the way they are, read the problem and think about what's happening in real life. Okay, so in this case, we have 75 newtons, that's a force. We need impulse, and we have a time. So there's only three things. That means we're going to use equation 1 here. So we're going to use J, F, and T as our variables. I did put the circle over here to remind you if we have to rearrange for any reason what that is. In this case, J, F, and T, since we're looking for impulse, that's going to be X. And to get impulse, it's a Newton times a second. So force's unit is newtons, times unit is seconds. So our unit for impulse will be a Newton second. The force given to us is 75 newtons, and the time is going to be 0.008 seconds. So that is our variables. Now our equation, we're just going to use the base equation since we're looking for J. So we're going to multiply force and time. So J equals F times T. We don't need to use the circle to rearrange it. So we're going to plug the numbers in where the variables are. So J is X Newton seconds. We're going to do force, which is 75 newtons. And we're going to multiply that by the time. And we're going to say that equals, so I need to multiply. And there we go. So I'm going to do 75 times 0.008. That's going to give us 0.6. And since it is a Newton second, a Newton times a second, that is our impulse. So remember, impulse numbers are kind of hard to understand. You might go, well, I don't really know what an impulse number is. But really think about the force, okay? That's really the idea, is the force acting on the object. If the force gets too high, then the object breaks. You can't have super high forces on specific objects. So that's why we talk about force and understanding how that might affect the object. So these numbers might not be, or well, the time will be more understandable, but the impulse, or the Newton seconds, you might go, well, I don't really know what that number turned out to be. So just thinking about it, increasing the amount of time the object contacts decreases the force. So if this number got higher, the time, so maybe we got into the hundredth of a second or tenths of a second, they were kicking it maybe a little bit less, then this number actually is going to go down, the force. Okay? All right, so for how long a time, so we're looking for time, must a tow truck pull with a force of 985 newtons on a stalled 2,500 kilogram car to give it a forward velocity of 3 meters per second. So notice in this case, we have a time we need, a force, a velocity, and a mass. So that's 4 variables, which leads us to looking at equation 2, a force, a time, a mass, and a velocity. Okay, so we need all of those variables. So some of you might say, well, I thought it was change in velocity. Well, it was at a stall, which means 0, and it now is at 3 meters per second. So 0 to 3 meters per second is 3 meters per second. So a lot of times we'll just tell you one velocity and you assume it started at 0 and ended at whatever given velocity there is. So it still is a change in velocity because the car was stopped and now it's moving. Okay, so we need F, T, M, and V. We need all of them. So our force is going to be given to us at 985 newtons right here. Our time is what we're looking for. So we're going to find X seconds. Okay. And our mass is given to us at 2,500 kilograms. And our velocity is given to us at 3 meters per second. So now we have a little different situation. I'm going to take the equation that we start with at top, and I'm going to put it down here so we can look at it. Now we have two variables on each side of the equal sign. We want to solve for only one of them, and it happens to be time that we want. So we're looking for time here. That means we need to get time by itself on this side of the equation. And that means we also have to get rid of force and move it to the other side. So to get rid of it and move it to the other side, we always do the opposite of what's happening to it currently. What's happening to it now is it's being multiplied by time. So to get rid of it, we do the opposite, which means divide it out. So we're going to divide out force, which will cancel force. And now time is by itself. What we do to one side, we always do to the other. So if we divided it out on that side, we have to divide it on the other side. So really what we did was we just took force and we moved it over to the other side. So time is by itself, and now we can solve for X, which is time. So our equation, I'm just going to write it a little nicer, is going to be time equals mass times velocity divided by force. So just plug them in. Time is X seconds equals our mass, 2,500 kilograms, times our velocity, which is 3 meters per second, all divided by our force, which is 985 newtons. So remember what we have to do is we have to multiply everything across the top. And we are going to do that first, and then we are going to divide it by what's on the bottom. So getting the calculator, we're going to have 2,500 times 3. You might know that 25 times 3 is 75, so it's going to be 7,500. And I'm going to carry over the units. A kilograms times a meters per second is a kilograms meters per second, because our units will work out too. Remember that. And that's a momentum unit. So now we have a momentum on the top. Divide that by a force, and that's 985 newtons. Oh, sorry. My thing was making noise, and I wanted to make sure it was still running. Let me move that out of the way. Okay, so the Newton, though, can be broken down into a kilograms meters per second squared. Just remember that. So what can we get rid of? The kilograms on top. Also, the meters per second here can be gone. And that squared means we have actually a leftover second. That's what the squared means. So that's exactly what we need is a second right here. So when I do my division again, I get 7,500. I'm going to divide that by 985. That's going to give me, I'm just going to move it down here because I'm out of space, 7.6, and we'll just go to 1. If we wanted to go one more for significant digits, we could. Even if you put 7.6, I'm going to be okay with that. The answer is 7.61 seconds, since it is a time. Okay, the next one is going to be, what is the mass? So we're looking for mass of a person running that has a change in velocity of 1.5 meters per second over 4 seconds if they apply 78 newtons of force to the ground. So again, we're back to the 4 variable one. Mass, okay, we have velocity, we have force, and we have time. So we're going to need all of them. Okay, so our force is given to us at 78 newtons. Our time is 4 seconds. Our mass is going to be what we're looking for, so x kilograms. And our velocity is given to us at breaking lead, 1.5 meters per second. So we need to rearrange our equation this time to get mass alone. So I'm going to write out the first equation that we always start with. Force times time equals mass times velocity. So we want mass alone. That means we need to get rid of V. So we always divide out what we need to get rid of, and we do it on both sides to move it over. So we're moving the velocity to the other side, so we have mass alone. So if I wrote it out again, I would have mass equals force multiplied by time divided by velocity, or change in velocity. So then I just plug it in. So I'm going to have my mass, which is x kilograms, and I'm going to have equals my force, 78 newtons, multiplied by, oops, let me move my screen up a little bit so y'all can see. Multiply that by my time, which is 4 seconds, divide it all by my velocity of 1.5 meters per second. So I'm going to multiply everything across the top first. So I'm going to multiply 78 times 4. That's going to give me 312 newtons times seconds is newton seconds. That's an impulse. See how these momentum and impulse things work out? I'm going to divide that by my velocity of 1.5 meters per second. So again, remember a newton second is a kilograms meters per second squared, so per second. And then we also have this additional second over 1. So this is really what we have on top. We have a lot on top. And then on bottom, we have just a meters per second. Ultimately, we need to get to a kilogram. Because of this second over 1 cancels those seconds, we also have this meters per second and this meters per second canceled. Boom, there's our kilogram. Okay, again, you do not have to do all this each time, but it's important that you understand that the units always work out as well. Kilograms what we need, so we know we're on the right track. 312, now we can divide it by 1.5. That's going to give us 208 kilograms for our mass. It's a person, and they're running. Okay. So I'm going to flip it over because I wrote the others on another page. Again, you can pause this, rewind this if you are feeling like I'm going too fast on your own at some point. Ooh, my camera's not going the right way. There we go. How much force? So now we're looking for force. Is put on a rolling chair that is pushed for 1.5 seconds and has an impulse of 12 newton seconds. So just for the sake of writing out my equations, again, I'm going to do that up here. Remember my impulse was J equals F times T. My second equation was my impulse equals change in momentum equation, which is F times T equals mass times velocity, or M times E. So looking at this, I only have 3 variables, force, time, and impulse. Means I'm going to use equation 1 here. I also need to rearrange it. My circle's on the front, so I'm just going to draw it again. J on top, force and time on bottom. So in this case, I'm going to write out my variables, J, F, and T. Those are what I need to solve this. J is given to me, or impulse, at 12 newton seconds. Force is not given to us. It's what we need. So I'm looking for X newtons. And my time is given to us at 1.5 seconds. So now I have to rearrange the equation. My base equation is J equals F times T, but this time I'm looking for F. So if I use the circle, I cover up the F and I get J divided by T. So force equals, because that's what I'm looking for, J divided by T. Now I just plug it in. So X newtons equals my J, which is my impulse, 12 newton seconds, divided by my time, 1.5 seconds. And we're looking for a newton. Our seconds cancel on top and bottom. And now I just do 12 divided by 1.5, and I get 8. And my unit is newtons. And I keep breaking that pencil. I'm out of control with that. Okay, well, let's do the last one. And we're talking about a ball. So an 8-kilogram ball is initially traveling at 12 meters per second. So let's underline what we have. 8-kilogram ball initially traveling at 12 meters per second speeds up for 25 seconds to a speed of 63 meters per second. Oh, look at that. They gave us two velocities. That's where that change in velocity comes in. How much force was applied? So they gave us a mass, a time, we're looking for force, and now we have two velocities. So that's what's really important up here. That's where that whole delta V comes in. Remember, because it is technically impulse equals change in momentum. So this change in momentum means you have to have a change in velocity. Usually I don't tell you two different velocities. We just assume it was 0 to whatever velocity we're given. But in this case, I gave you a starting velocity and I gave you an initial or ending velocity or final velocity. So we need to do a little math to get our change in velocity is what we need. So remember our equation, force times time equals mass times, I'm going to just put the change in there just so we remember. And we have a force, a time, a mass, and in this case, we have an initial velocity and we have a final velocity, okay? And those together are going to give us what we need, which is our delta V. So once we get these worked out, we're going to put the answer down here in delta V. So our force is given to, or is not given to us, it's what we need, x newtons. Our time is 25 seconds. Our mass is 8 kilograms. So now we need to use the initial and final velocity so we can get our change in velocity. Oops, I know you guys can't see that down there now that I look at my screen. So our initial velocity is what it starts at. It starts at 12 meters per second. And our final velocity is what it ends at, 63 meters per second. So remember, to get change in velocity, we have to do final velocity minus initial velocity. And so we're going to do that. Final velocity, 63 meters per second, equals minus 12 meters per second. So if we do 63 minus 12, you're going to get 51, right? So that is going to mean our change in velocity is going to be 51 meters per second. So now we have all the variables. We have force, time, mass, and change in velocity. So we're going to kind of ignore this middle section. We're going to look at this new one that we have, this new change in velocity. Now that's not it though. We need to get force by itself on this side of the equal sign. So if we need to get force by itself, we now have to get rid of t. To divide out t to get rid of it leaves force by itself. We do it to one side, we got to do it to the other side. So now we're going to have force equals our mass times our velocity, our change in velocity that we just found, divided by our time. Okay, let's plug it in. So our force, x newtons, equals our mass, 8 kilograms, times our velocity, which is the change in velocity that we need, 51 meters per second, divided by our time, which is 25 seconds. So we get equals, we got to multiply everything on the top first. So 8 times 51 equals 408. Remember, kilograms times the meters per second is a kilograms meters per second. Now we're going to divide that by 25 seconds. Now, some of you might say, wait, don't things cancel? This second here is on the bottom of the meters, and this second is on the bottom of the equation. They don't cancel each other because this second can't cancel out. What this is doing is giving us, and I'm going to just put it over here, just the unit. It's giving us a kilogram meter per second over top of another second. What's that? That's a kilograms meters per second squared And what is a kilograms meters per second squared? A kilograms meters per second squared is a Newton. Remember that? So that's what we need. That's how we got the Newton out of this. A kilograms meters per second is a kilograms meters per second squared, which is a Newton. All right, but let's do the actual numbers. 408 divided by 25 equals, let me try it one more time because my phone was slow. There we go. 16.32 newtons. That is the force that is applied to the ball in order to get that change in velocity. Okay? And that is it.